Okay, so after a long time we are back with number theory, and the last thing we saw was the Goldbach conjecture. And today in fact we are going to prove that there are infinitely many primes of the form 4n plus 3. That is, if you divide these primes by 4, the primes leave the remainder 3. That kind of prime. Okay, and the number of such primes is infinite. That's what we are going to prove today. But before that though, there is a discussion where we have a little bit of history on some problems related to the Goldbach conjecture. And one problem related to the conjecture asks whether every even number is the sum of two almost primes. And the first result of this kind was found by Burton. Okay, by the way, what do we mean by an almost prime? An almost prime is not necessarily a prime, but it's a product of a certain number of prime factors, a certain number of prime numbers. The less the number of primes in such a number, the better the result. And the first result of this kind was found by the mathematician Burton. Who in 1920 proved that if n is a sufficiently large positive even integer, then n can be written as a sum of two integers a and b, which are almost prime in the sense that each one of them has at most 9 prime factors. In that sense, they are almost prime. And this result was improved by Alexander Buxton in 1940. And his improvement was that this A and B actually, such A and B exist where each one of them has at most 4 prime factors. Okay, so that's an improvement because the number of prime factors has been brought down. So in Burton's result, it's at most 9. In Buxton's result, it's at most 4. Then in 1948, the Hungarian mathematician Renai, I am not sure whether I am pronouncing these names correctly. Okay, these are some foreign names. But if I am butchering these names, then I am apologizing, okay. So what Renai showed was that every sufficiently large even positive integer n can be written in this form. For some r, where this p and all this pi are primes. How is this an improvement of the previous results? It's also a kind of, that kind of result where n has been expressed as a sum of two almost primes, but here one of them is actually a prime. So that's why it can be called an improvement. However, in Renai's original proof, R is very large. I haven't seen the proof myself, so I have no idea in what sense R is very large. But most likely an actual value of R has not been given. Maybe some bound of R is given. I hope so. Okay, it's usually like that. But then what mathematicians did after this is that they tried to improve this result by bringing down the size of R. Can we find smaller and smaller R? So that will then improve this result, and the first improvement was done by Wang, someone named Wang, who in 1959 found this improvement, where r is less than or equal to 4. So obviously this is not very large. I mean, when the author, when Burton is saying that r is very large in Renai's proof, actually it will be in some sense very large, but this then should be a significant improvement to that. However, even this was also improved by A.I. Vinogradov. Who in 1965 proved that r can be considered to be less than or equal to 3. Now, looking at these 2 bounds, this may not seem like much of an improvement, but you see these years, and given how bright Vinogradov is, if you know about him, this becomes significant because it is likely very difficult to bring this down from 4 to 3. At least I think so. Okay, so just by looking at this, we should not think that it's almost nothing. But even this was also improved by Chen Jing Ran in 1966, the very next year. And he showed that r is less than or equal to 2. Maybe Ran saw something in the proof that Vinogradov failed to see. Maybe, I don't know. Okay, because the very next year it came out, no? So that's fine. Now, if someone is able to show that r is less than or equal to 1, then r has to be equal to 1. And that would bring us towards the Goldbach conjecture again. Now, it seems like everything that has so far been proved points us towards the fact that Goldbach's conjecture should be true. It is true. However, we still do not have any proof that it is true, despite having this overwhelmingly positive evidence in favor of it. And in fact, Vinogradov himself proved something else about the original Goldbach conjecture itself. What he showed is that if A of x is the number of positive integers n less than or equal to x, which are not sums of 2 primes, that means which do not obey Goldbach's conjecture, which refute the conjecture. If A of x measures the number of such integers not exceeding x, then Vinogradov showed this limit limit of the ratio of A of x to x is 0 as x approaches infinity. How to interpret this limit? This limit can be interpreted by noting what A of x actually is. A of x measures the number of it's like you are saying something and many people are not believing in that. Okay, A of x measures the number of people who are against you, the number of integers who are against Goldbach's conjecture, against the truth of Goldbach's conjecture. that number is growing in relation to x so slowly that eventually the limit becomes 0. So an interpretation of this limit can be given like this. In fact, Edmund Landau put it very aptly. He said that the Goldbach's conjecture is false for at most 0% of the integers, even integers of course. However, this at most 0% does not exclude of course the possibility that there are infinitely many exceptions. Alright, so that's just about it that we have in this text. I mean, of course, in the actual research literature, there will be many more things related to these things. But in the text, we have till this. After this, the author goes to the question of proving that there are infinitely many primes of some special form. We already know the division algorithm tells us that all the positive integers can be divided into 4 classes according to these forms, right? 4n, 4n plus 1, 4n plus 2 and 4n plus 3, depending on what remainder an integer leaves when divided by 4. There are 4 remainders 0, 1, 2 and 3, and accordingly we have these 4 forms for any integer, and any given integer assumes precisely one of these 4 forms. Now we know of course that we have the even integers divided into 2 classes, and they have either the form 4n or 4n plus 2. Any even integer, if you divide by 4, it leaves either the remainder 0 or 2. And that means the odd integers leave the remainders 1 or 3 when divided by 4. Now among all the primes, we have precisely one even prime, which is 2. All the other primes are odd integers. And accordingly, they get divided into 2 classes like this: primes of the form 4n plus 1 and primes of the form 4n plus 3. So what the author did, the author wrote some first few primes of each of the forms, and they are like this: 4n plus 3, 4n plus 1. Okay, one below the other. And let us just see what these are. 3, 7, 11, 19. It will be a little difficult to write it this way here. Instead, I think, okay, to just see something about why are we going to write a few of the first primes of this form. That can only be seen if I am able to write it at once. So instead, let me write it like this vertically: 4n plus 3, and on this side say I have 4n plus 1. Three, 7, 11, 19, 23, 31, 43, 47, 59. Won't be able to write everything here itself. I will continue from there. 67, after 67 we have 71, 79 and 83. And if correspondingly we also write primes of the form 4n plus 1, then we get these primes 5, 13, 17, 29, then 37, 41. After the 43 has gone there, so we have 53, 61. $73, 89. Okay, that's just it. I mean, that's just it means, of course, only this many we are showing. There are others. Now, a function was devised to kind of see how many primes there are of a given form less than or equal to a given number, and that we denote by this function pi a comma b of x, and this denotes the number of primes of the form an plus b not exceeding x, that means less than or equal to x. Not exceeding x. So from our little table, what do we find? We find that pi 4 comma 1 of 89 is equal to 10, but pi 4 comma 3 of 89 is equal to 13. In other words, the number of primes of the form 4n plus 3 and less than or equal to 89 is 13. We can count in this table, whereas those of the form 4n plus 1 less than or equal to 89 is 10. Okay, now these two values may make you think that this is less than, of course, in this case this is less than this, but is it always going to be the case? Is it the case that pi 4 comma 1 of x is less than or equal to pi 4 comma 3 of x always for every x? Well, not necessarily. In a letter in 1853, Chebyshev guessed that Chebyshev guessed exactly that for small values of x, and he implied that this should be true for all x. Okay. However, that turned out to be false. Again, we are saying some history, but that's the kind of thing with this book. Here and there, it's a nice thing. Actually, we get to see what went on, and I mean, without these things, we would just simply be going through the results somewhat in a dry manner, without knowing at all what went on behind the scene. Who are the people who found these things? What went on when these things came out? So it's nice to have a little history always. So Chebyshev implied that he had a proof of this fact that this inequality is true for all x. However, in 1914, J.E. Littlewood proved that this inequality actually fades. That means the reverse inequality is true for infinitely many times. And J.E. Littlewood, let us recall, you may already know that he was an associate of Godfrey Harold Hardy. Ramanujan, Hardy, Littlewood. So that trio, we are talking about them. So he proved that there are infinitely many instances in which this inequality fails, but he was not able to give a value of the first x for which this fails. However, a computer search found that the first x where the opposite inequality is true is this. It actually turned out to be quite difficult to find what the first x is. So after all, a computer found it, not any human being. Okay, computer through extensive search, because computers search each and every case. In some situations, they search each and every case because they are so fast, they are able to find these things. The next prime where the exact inequality happens, where the exact opposite inequality happens is a larger value, which is 616841, and it turns out that the opposite inequality continues to be true means it is true for the 410 million successive integers lying between two gigantic numbers. It's nice to see these things, but after some time it becomes a little boring to go through these bits and parts of results without actually seeing something. I'm not going to say anything more on this, okay? You can see in the text. There is something about primes of the form. These instances also. Something is there in the text about some inequality between these two things. Instead, let us come to the actual result that we are going to prove today. Namely, we are going to prove that there are infinitely many primes of the form 4n plus 3. But before that, we have a lemma, an elementary lemma, which will be used in the proof. And the lemma simply says that the product of two or more integers of the form 4n plus 1 is also an integer of that form. And its proof is very easy. You consider two such integers and take their product and show that the product is also of that form. And from that case where we have two such numbers, you can have a product of any number of such numbers, and that result follows by induction. So let's see the case of a product of two numbers of the form 4n plus 1. So as a proof, I am just going to give the idea. Say one of them is 4n plus 1 and another is 4m plus 1. N and m are integers. If you actually carry out the multiplication, you are going to get 16nm plus 4n plus 4m plus 1. from the first three terms you can take 4 common out. That leaves you with 4nm plus n plus m plus 1. Since 4nm plus n plus m itself is an integer, so the product is again of the form 4 times an integer plus 1. That's it. And now we come to the main result of today. Theorem 3.6, and its proof is going to remind us of the proof of Euclid's actual result, that there are infinitely many primes. It's that kind of proof. There are an infinite number of primes of the form 4n plus 3. Proof. So just like Euclid's original result and its proof, we are going to suppose that there are only finitely many such primes. Suppose there are only finitely many such primes. Finitely many primes of the form 4n plus 3, and let them be these, say q1, q2 and so on, qs, where s is some positive integer. And just like Euclid's proof, here also we are going to use them to construct a number, and from that number we will derive some kind of contradiction, and that number is 4 times the product of this minus 1. Now consider the following integer: n equal to minus 1. Okay, and note that actually this number capital N is of the form 4n plus 3. How is it of that form? If you multiply, then you will get 4 times this minus 4 plus 3, which is minus 1. Alright. Now obviously n is greater than 1, because we can see that this thing is non-negative. Actually n is greater than or equal to 3. Since n is greater than 1, by the fundamental theorem of arithmetic, n has a prime factorization and ordinary prime factorization. Not of the form 4n plus 3 or 4n plus 1, not like that, an ordinary prime factorization. N has a prime factorization. say R. Okay, all right. Now what can we say about these primes pi? Note that because of the form that capital N has, capital N is odd, it is not even, and that is why in this prime factorization no pi is the even prime too, none of them, since N is odd, pi is not equal to 2 for each I. That means each pi is an odd prime, and so each pi is of the form 4n plus 1 or 4n plus 3. Thus, each pi is of the form 4n plus 1 or 4n plus 3. We don't really know how many of them are of the form 4n plus 1 and how many of them are of the form 4n plus 3. Maybe all of them are of the form 4n plus 3. However, all of them cannot be of the form 4n plus 1. Why? That's because by the previous lemma, if that is the case, then capital N itself should also be of this form. But capital N is not of the form. Capital N is of the form 4 times some integer plus 3. It's not of the form 4n plus 1. So by the previous lemma, all of the pi's cannot be of the form 4n plus 1, or equivalently at least one pi must be of this form. Pj is of the form 4n plus 3 for some j. Okay. However, we only have these primes. According to our supposition, these are the only primes of the form 4n plus 3. So now this pj has to be equal to one of them. We have no other choice. But then Pj is equal to Qk for some k. Alright, so now we are almost there. Note that on one hand, Qk of course will appear here, because it is one of the Qi's. So Qk divides this product 4 times this, obviously. But at the same time, since Qk is equal to Pj, Qk appears here as well, and as a result Qk divides capital N also. So Qk divides N as well as this. And what can we conclude from that? Let us first write this fact. This implies Qk divides N and Qk divides this. But then Qk would also divide their difference . but this is not possible. It's not possible because no prime divides 1. But that's impossible. And this impossibility is a consequence of our supposition that there are only finitely many primes of the form 4n plus 3, which must thus be false. And that proves that there are infinitely many primes of the form 4n plus 3. So that completes the proof. Actually, this raises another question. That question is whether there are also infinitely many primes or finitely many primes of the form 4n plus 1. Actually, of the form 4n plus 1 also there are infinitely many primes. However, at this very moment we do not have the tools necessary to prove that. We have to wait for the development of those tools. There are some other things also regarding primes and their properties in this section. We are going to see that in the next number theory upload. So that's just it for tonight, folks. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.